Chemistry class. Coordination compounds. Imagine you're at a party where one popular person, let's call them Alex, is surrounded by friends holding their hands. Alex is at the center, and friends are arranged around them. This is exactly how coordination compounds work.
In chemistry, coordination compounds have a central metal atom, like Alex, surrounded by molecules or ions called ligands, like the friends. These compounds are everywhere, in the hemoglobin in your blood, the chlorophyll in plants, and even in some medicines.
The deep blue color you see in copper sulfate crystals comes from coordination compounds where copper is the central metal surrounded by water molecules. Ligands are atoms, ions, or molecules that donate electron pairs to the central metal. Think of them as generous friends who share their belongings, electrons, with the metal. Ligands can be classified by the number of donor atoms they possess, such as Monodentate, 1 donor atom, or Polydentate, 2 or more donor atoms. Examples in chemistry include water and ammonia. Bidentate can form 2 bonds and Polydentate can form many bonds. Coordination number is simply how many ligands are directly attached to the central metal, like counting how many friends are holding hands with Alex at our imaginary party. Here in the example, tetraamine copper 2 ion, the coordination number is 4. Coordination number 2 results in a linear geometry. Coordination number 4 can result in either tetrahedral or square planar geometry. Coordination number 6 results in an octahedral geometry. Why coordination compounds have colors? When light hits these compounds, the metal's electrons get excited and jump to higher energy levels. The color we see is the light that wasn't absorbed. Ruby's red color comes from chromium coordination compounds. Magnetic properties. Some coordination compounds are attracted to magnets, paramagnetic, while others are repelled, diamagnetic. This depends on whether the compound has unpaired electrons, like having odd or even numbers of people in a dance. Shapes of coordination compounds. Just like different dance formations, coordination compounds have specific 3D shapes. Linear, like people standing in a straight line. Tetrahedral, like a pyramid with triangular base. Square planar, like 4 people sitting around a square table. Octahedral, like 6 people arranged around a cube. IUPAC nomenclature. The naming system. Naming coordination compounds follows specific rules, like addressing someone formally. 1. Name the ligands first, alphabetically. 2. Add prefixes for multiple ligands, di, tri, tetra. 3. Name the central metal. 4. Add the oxidation state of metal in Roman numerals. Bonding theories. Bonding theories for coordination compounds were developed to explain bond formation, shape, magnetism, color, stability, and reactivity. Things that simple bonding models, like Lewis structures, cannot explain. Werner's theory, the pioneer, Alfred Werner was like the first person to understand how our party analogy works. He proposed that metals have primary valence, like their main personality, and secondary valence, their ability to make friends with ligands. Valence bond theory, VBT. This theory suggests that metals use their empty orbitals, like empty seats, to accommodate electrons from ligands. The metal rearranges its orbitals to make room for guests. Crystal field theory, CFT. This theory focuses on how ligands affect the metal's electron arrangement. Imagine ligands as people standing around the metal, creating an electric field that influences how the metal's electrons behave. Structure and stereoisomerism. Coordination compounds can exist in different forms, like how you can arrange the same furniture in a room differently. Geometric isomers. Different spatial arrangements, cis and trans. Optical isomers. Mirror images that can't be superimposed, like your left and right hands. Importance of coordination compounds in real life. 1. Qualitative analysis. Coordination compounds help identify unknown substances. Example, adding ammonia to a copper solution produces a deep blue color, confirming copper's presence. 2. Metal extraction. Many metals are extracted from ores using coordination chemistry. Example, gold is extracted using cyanide, which forms a stable coordination compound with gold, allowing it to be separated from rock. 3. Medical applications. Cisplatin treats cancer. Iron supplements treat anemia. 4. Biological systems. Coordination compounds are essential for life. Hemoglobin. Iron coordination compound that carries oxygen in your blood. Chlorophyll. Magnesium coordination compound that helps plants photosynthesize. Everyday examples. Photography. Silver halide coordination compounds in old film photography. Water treatment. Iron and aluminum coordination compounds remove impurities. Paints. Titanium and chromium coordination compounds provide colors and durability. Fertilizers. Many contain coordination compounds to provide essential metals to plants. Video by Anand Mohandas.